Good day, welcome to One-on-One Maths Private Tutors. Today we are going to do ray diagrams to see how light is reflected and refracted in mirrors and convex lens. We are also going to talk about the meaning of real images and virtual images and see how these are obtained. First, we'll start with the mirror. A mirror works on the principle of reflection. We'll look at a plane mirror. For example, let's have our plane mirror. We have our mirror here. And then we have an object over here. We are interested to see how rays of light move from the object to the mirror and bounce off the mirror, and someone can see. It might appear that the image is in the mirror, but it's a matter of light rays bouncing off, being reflected off the surface of the mirror. So this is our mirror. We are going to draw ray diagrams. This might be a requirement in paper 2 to draw the rays. So we'll take step by step how these light rays move from the object until we finally see an image. And we'll also explain why we say the image is virtual on a plane mirror and not real. So a plane mirror works on reflection of light waves, and the image formed is virtual. And from experience of using a mirror, we know the image is laterally inverted, which means left becomes right and right becomes left, but it's upright and it's same size. So the image has these 4 characteristics. Image is virtual, the image is laterally inverted, the image is upright, the image is the same size as the object. But our main task here is to trace the rays and see where the image falls. Explain why we say it's virtual. Most important thing is virtual here. That's the main point we want to explain. If we have rays coming from the object, they will come to the mirror. What we are interested in, so these are incident rays. We want the reflected rays. Another ray can come from the mirror at this point. At any point, a ray can come to the mirror and it is reflected. So we have these 2 rays. What we are interested in is their reflection. From the principle of reflection, angle of incidence is equal to angle of reflection. What we want is a normal so that we can measure the angle of incidence and construct angle of reflection. What we do is we take our compass, construct our normal there. There is our 90-degree point. We take our ruler, join. Now we have our normal there. We can also construct a normal there, parallel to that. So what is a normal? A normal is a line that is perpendicular to the surface. This is the surface of the mirror. So we have this angle here as being 90, this angle here as being 90. These are 2 parallel lines. What we have just done is to move our ruler without changing its slope. And then we have our 2 normals. This is a normal to this incident ray. This is a normal to this incident ray. Now we want to measure the angles of incidence there and there so that we can construct angles of reflection. So we take our protractor, 28 degrees there. So we have 28 degrees there. That's our measurement from this inner scale. We would want 28 degrees to be our angle of reflection because angle of incidence is equal to angle of reflection. So we turn our protractor and measure from the normal angle of reflection, 28. 28 degrees is there. Now we join. So this is also 28 degrees. That's my angle of reflection. The next thing I might want to do is to measure this angle of incidence, which is between this incident wave and the normal. This angle is 40 degrees. Now I want the angle of reflection, which is 40 degrees from the normal. Remember, angle of incidence is equal to angle of reflection. That is the law of reflection. So here I'm going to measure 40 degrees, which is here. Now I have to join these 2 points. And this angle is 40 degrees, angle of reflection. Now we have this reflected ray and that reflected ray going from the mirror. So we have incident ray, which has been reflected, incident ray, which has been reflected. Now, these rays are not meeting. We can see they are growing apart. We might need to trace them to see where they meet. We trace them back to see where they meet. So we take this reflected ray and we trace it back. And also this reflected ray and trace it back. Where these two meet is where our image will be. So we can put image there. What does this mean? When rays fail to meet and we have to trace back to find the image, that is what we call a virtual image. If these rays were to meet, let's say we had this ray and that ray coming to meet there, then we would have a real image. But these rays are failing to meet and they are growing apart, and we would have to trace them back using these virtual lines, which are not the rays themselves, to locate the image. That is what we call a virtual image. Now we go to converging and diverging lenses. Lenses are used in optical instruments such as cameras, spectacles, microscopes, and telescopes. Lenses use the principle of refraction, which is the bending of light. That is, they allow light to come in and then they change the direction of the light. For a converging lens, light is bended inwards. This is an example of a converging lens where light is bended inwards. For a diverging lens, light is bended outwards. So this light coming in will be bended outwards. That is the difference between a plane mirror, which uses reflection, and lens, which allow light to come in and then change their direction. A converging or convex lens is thick in the center. So this is a converging lens and it bends light inwards. All this parallel light is bending inwards towards what we call the focal point. So all parallel light that is coming in should converge. That's why it is called a converging lens. Should converge at a point which we call the focal point. We need also to understand that the line that is in the middle of the lens, that passes through the middle of the lens, is called our principal axis. So we use this as a magnifying glass or a burning glass. The distance between the center of the lens and the focal point is what we call the focal length. Let's look at this question. In the space below, draw a ray diagram to locate the image of an object of height 1 centimeter placed 5 centimeters from a convex lens of focal length 2 centimeters. Draw your diagram full size. You are advised to locate the lens roughly in the center of the space. First, we have our principal axis, which is this horizontal line, and we need to construct our perpendicular, which will be the center of the lens. So it should be 90 degrees. This is our center. Our 90-degree point will be there, and our point C will be there for the center of our lens. Now we connect using a ruler. So this is our lens, our convex lens. It will be like that, okay? But we don't need to draw it. What we just need is the center line of our lens. Then we have our focal point. We are told in the question, focal length is 2 centimeters. So we measure 2 centimeters from this center. 2 centimeters is here. And we might also want 2 centimeters here. So this is our focal point F. The object is of height 1 centimeter, placed 5 centimeters from a convex lens. So the position of our object is 5 centimeters. We measure 5 centimeters from the center. The object is 1 centimeter high. So again, we use our ruler, measure 1 centimeter. So this is 1 centimeter there. Now we need 3 rays. One from the top of the object going parallel to our principal axis, horizontal line. We take it up from there, then we draw our ray. This is our first ray. When this ray gets to the center of our lens, it is converged to our focal point. So that's the second ray, the refracted ray. It is refracted to our focal point. Okay, so this is our second ray. 1, 2. And we need another ray from the top of the object through the center of the lens. That one is not refracted. It goes straight through. So this is our ray. Only need 1, 2, and 3 rays. Where these rays meet, that's where we have our image. So our image, there is our image. This is our object, symbol O. This is our image, symbol I. So what can we say about this image? This object is upright like this. This image is inverted, okay, which means it's upside down. If this is upright, this is upside down. So we call it inverted. Our image is real. Why do we say that? Because these rays are actually meeting there. This incident ray is refracted and it goes that way, and this one goes through unobstructed and they meet. So the image is real. Let's look at the size. If this is 1 centimeter, the image we are seeing it's 0.7 centimeters. So it's diminished, which means our image is smaller. Virtual images can also be formed on a converging lens if we place our object between the center of the lens and the focal point. Let's do an exercise to show that. Measure 1 centimeter of our object. This is our object. Let's see how these rays. First ray is the one parallel to our principal axis. We divert that to the focal point of our first ray and our diverted ray. Then we have the one passing through the center. Now, in this case, we can see these rays are not converging, are not meeting up, they are diverging. So what do? We retrace them back there and also there. Where they meet there, we can create our image. This is our object. The rays from the object are not meeting. Then we retrace them back to create our image. What can we say about this image? It is virtual because these are trace back rays. It is enlarged and it is upright. As we can see, this is upright, this is upright. So in conclusion, we can say if the object is between the center of our lens and the focal point, then the image will be virtual because the rays will not meet, we'll have to trace them back. If an object is beyond 2f, as in the case with our first question where it was 5 centimeters, f was 2 centimeters, 2f is 4 centimeters, and this is 5 centimeters. We saw that our image is real, inverted, and diminished, which means it's smaller. If the object is at 2f, it will be real, inverted, and same size. If our object is between f and 2f, it will be real because these rays actually meet. It will be inverted, upside down, and it will be enlarged. You can say this is bigger than that. So that's it about objects and images for plane mirrors and lens. So we have done the ray diagrams. Thank you.